This video is going to review the concepts and calculations for gases for chemistry class. It involves pressure, temperature, volume, moles, and common things that involve with gases, along with some gas stoichiometry at STP and non-standard conditions. Let's get started. So a piston pushing with a force of 115 newtons over an area of 0.05 meters squared. So we just divide those two. Pressure is force per area, so 115 divided by 0.05 to give us 2,300 newtons per meter squared, or pascals. Now to go from Celsius to Kelvin, we just add 273 to that. So if I want to convert 35 degrees Celsius into Kelvin, I just take 35 plus 273 to give me 308 Kelvin. Now what about our concepts? What if the pressure of a gas increases and the temperature has to change with that, but everything else remains constant? Well, if pressure increases, that means the temperature increases. So this is Guy-Lussac's law, the idea that molecules move faster, they collide with more forces, creating a greater pressure. Now what if the volume of a gas increases and we're trying to figure out what happens to the pressure? So now everything else is constant. So to increase the volume of a gas increases, that means there's more space for molecules to bounce around, therefore pressure decreases. And that's Boyle's law. The volume of a gas decreases, what happens to the number of moles of the gas? So if volume decreases and everything else remains constant, that means the number of moles has to be smaller. And that's the ideal gas equation. Let's continue. The temperature of a gas increases and the volume decreases. What happens to pressure? So now we have temperature changing, we have volume changing, and pressure. So this is the combined gas law. Okay, what happens? So if the temperature of a gas increases, that's likely to increase the pressure. And the volume decreases, that also is likely to increase pressure. So I'm going to go increases on that. And that's the combined gas law, because both of those factors does increase the gas pressure. Next, the temperature of a gas decreases. What happened to the volume of the gas? Well, if everything else remains constant, the molecules are moving slower, therefore the volume will get smaller. It decreases, and that's Charles' law. All right, let's go on to calculations now for part 3. So we have a gas at a volume of 3.5 liters, 88.5 kilopascals, and 20 degrees Celsius. We want to determine the number of moles for this particular gas. Well, we're going to use ideal gas law. Pressure times volume equals number of moles times the gas constant times temperature. So then I put my 88.5 right here for pressure, 3.5 for volume, N is my moles I'm trying to solve for, 8.31 is my gas constant for kilopascals. And of course I convert my temperature into Kelvin and I place it there. And then I just solve for N. I'm going to take 88.5 times 3.5 divided by the combination of 8.3 times 293. Okay, a gas has a volume of 45.5 milliliters at 95 kilopascals and 30 degrees Celsius. Determine the volume at standard temperature and pressure. That's what STP stands for. So standard pressure is 101.3 kilopascals and 273 Kelvin is standard temperature. So we're just going to put numbers into our equation. Pressure 1, 95. Volume 1, 45.5. Temperature 2, we know is at our standard, 273. Equals pressure 2, our standard, 101.3. Volume 2, we don't know. And temperature 1, of course, we have to convert to Kelvin, is 303. And then we just solve for volume 2, 38.4 milliliters. The gas has a pressure of 55.6 kilopascals at 50 degrees Celsius. Determine its temperature when the pressure is changed to 77.6 kilopascals. So this is Guy-Lussac's law. Put your pressure 1, 55.6 times temperature 2, which is what you're trying to find. Pressure 2 is 77.6, and temperature 1 was the 323 once you convert Celsius into Kelvin. And then solve for temperature 2. A gas has a volume of 66.7 milliliters at 85 kilopascals. Determine pressure of the gas when its volume doubles. This is Boyle's law because pressure and volume are the ones mentioned. So P1 V1 equals P2 V2. So we put our beginning pressure there, 85, our beginning volume 66.7, and we put a doubled volume for our volume 2 and then solve for pressure. We'll see that volume, the doubling of the volume caused the pressure to go down by a factor of 2. All right, a gas has a volume of 99.5 milliliters at 30 degrees Celsius. Determine the volume at standard temperature. Well, this is Charles' law because we're looking at volume and temperature. So volume 1, 99.5. Temperature 2 is our standard 273. Volume 2 is what we're trying to find. And temperature 1, once we convert to Kelvin, which is over here, is 303. And solve for volume 2, 89.6 milliliters. All right, now our last questions to deal with are stoichiometry. Okay, standard conditions first. The liters to liters type of calculation at STP. So we have 25.6 liters of propane. Okay, will require how many liters of oxygen, okay, at STP? Well, let's go back up and look at our balanced equation. For liter to liter, all we need to do is multiply by the mole ratio from the chemical equation because we're not changing anything from 2 moles. Everything's in liters. Okay, so I'm starting with 25.6 liters of propane, C3H8. I'm just going to say, well, what number is in front of my oxygen? 5. So I put a 5. What number is in front of my propane? A 1. So we just times it by a 5-to-1 ratio from the chemical equation. And that gives us 128 liters of oxygen. And you're going to see that's what we're going to do for these next 2 questions. These are all liter to liter calculations. And all we got to do then is for 17.7 liters of oxygen, we're trying to find liters of CO2. I'm going to times that by 3 for my carbon dioxide, divided by 5 for my oxygen right there. All right, and one more of these. 42.5 liters of carbon dioxide are produced. How many liters of propane reacted? So I take my 42.5 and I times this by 1 because there's a 1 in front of C3H8 and divided by 3 because there's a 3 for my CO2. And please notice again, whatever you're solving for goes on top. Whatever you give, it goes on the bottom. Okay, now what if I'm going from grams, okay, to liters? 18.8 grams of propane will produce how many liters of carbon dioxide at STP? Now this is a 3-step question. First, I'm going to take my 18.8 grams of propane times 1 mole over its molar mass. 3 carbons and 8 hydrogens is 44. I'm going to times it by the mole ratio from the chemical equation. We can go back up there really quickly. There's a 3 for my CO2 and a 1 for my propane. And how do I get out the liters then? Well, 1 mole of any gas at STP always occupies 22.4 liters. So then I'm going to take that and multiply by 22.4 liters of CO2 over 1 mole over CO2. And bang, there your answer is 28.7. Now what about the next one? 14.4 grams of propane will require how many liters of oxygen? Same thing. Take my grams, multiply by 1 mole over the molar mass of it, times by 5 over 1. There's a 5 in front of the O2 in the equation, and 1 mole for our C3H8. And again, times it by 22.4 liters of oxygen per 1 mole of oxygen. Because remember, 22.4 liters is the same for all gases at STP. Now, what if we are now going to be at non-standard conditions? So how do we handle that? Well, we have to use ideal gas law. The ideal gas law is used. So you're going to find that the steps are the same. So if I have 32.2 grams of propane